The widespread use of smartphones and data rate-intensive applications like HD video streaming have led to a dramatic increase in mobile data traffic. To satisfy this demand, new network technologies are required. The European research project iJoin investigates two of the most promising concepts. One is to deploy large numbers of very small base stations, leading to less users per cell. Another is cloud processing. Borrowing from the concept of cloud computing, cloud-based mobile networks use central baseband processors that run on virtual machines, on off-the-shelf server hardware. This enables new cooperative algorithms, simpler network management, as well as lower cost and energy consumption. Embracing these two trends, a part of the network that has so far not received much attention becomes a key element: the so-called front-haul and backhaul links that connect the base stations with the centralized processors. Since the small base stations can be deployed anywhere, from lampposts to building walls to billboards, the backhaul cannot always be provided by a wired connection. Instead, high-speed wireless technologies utilizing millimeter wave frequencies can be used. In order to prove the concept of high-speed wireless backhaul and to be able to test innovative algorithms using a realistic backhaul, Dresden University of Technology has developed a testbed for iJoin using a 60 GHz wireless link.
Most technologies focus on improving the access link between users and base stations and assume the backhaul to be perfect. But since the backhaul actually might be a key bottleneck in cloud-based networks, we need to evaluate whether our new algorithms also work when using a real-life, realistic backhaul. This is what we're able to do with our joint access and backhaul testbed.
The testbed consists of two parts: a laptop PC that simulates users, base stations, and cloud processors, implementing, for example, an innovative algorithm that improves the access link. The second part is a real-life wireless backhaul link, acting as hardware in the loop. The wireless link itself features two components, both at the receiver and at the transmitter: a digital baseband and an analog front end. The digital baseband is implemented on FPGAs using a 1-bit analog-to-digital converter and a massive parallelized implementation to ensure an energy-efficient design. It implements packet synchronization, link loss detection, differential QPSK modulation, an optional forward error correction using convolutional code, and a MAC layer protocol. The analog front ends consist of horn antennas, filters, up and down converters, and a limiting amplifier.
The 60 GHz band is ideal for wireless backhaul over short ranges of a few hundred meters. It offers up to 9 GHz of bandwidth to achieve multi-gigabit per second of throughput. And operators don't need a license to use it, so it can be deployed very fast and at low cost. But of course, wireless links also have their disadvantages compared to wired connections. Wireless links are attenuated by free space path loss and also by varying outdoor conditions, as for example rain.
This attenuation means that bit errors are introduced into the backhaul that harm the overall performance of the transmission. The conventional way to avoid this is to introduce an error protection code. However, the encoder in turn introduces undesired latency and also decreases the backhaul's throughput because additional redundant information has to be transmitted. In iJoin, we therefore use a different, innovative algorithm for what we call joint access and backhaul decoding. The access link already introduces Gaussian noise to the transmitted data. Modern receivers use the knowledge about the Gaussian distribution to optimally detect signals. However, if additional bit errors are introduced during the backhaul transmission, the distribution is no longer Gaussian, which means a conventional receiver can no longer reliably detect a signal. But using an advanced receiver developed within iJoin, we can factor the backhaul errors into the distribution and thus ensure a reliable transmission even when the backhaul is imperfect. This is just one example of the algorithms we implemented in our testbed. It shows how important it is to pay special attention to the backhaul when dealing with cloud-based networks. With our testbed, iJoin can now evaluate such new approaches using a realistic backhaul link.